In question number 6, a uniform rope of mass m and length L lies on an inclined plane which makes an angle theta with the horizontal. The top end of the rope is nailed on the plane. The coefficient of friction between the plane and the rope is mu. The tension at the top of the rope is, and it is given in the question, assume that the rope will slide if set free. So it is already given in the question that if the nail is removed, then the rope will move down the incline. So at that moment the static friction will acting. So at that moment limiting static friction will be acting. So I can say that, so if I draw the free body diagram, then mg sin theta will act in this direction, mg cos theta will act in this direction, maximum value of static friction will act in this direction, that is mu into n, and the value of normal reaction is equal to mg cos theta. And let tension T is at the top of the end of the rope is acting in this direction. So if this rope is in equilibrium, I can say that the value of T is equal to mg sin theta minus mu into mg cos theta. So from here I can say that if I take mg common, so this is equal to sin theta minus mu cos theta. So option 1 is the correct answer. Let's move to question number 7. In question number 7, a point mass M is hanging from two ideal strings as shown below. The ratio of tension T1 to T2 is, so it is given in the question, the point mass is in the state of equilibrium. So if I draw the free body diagram, then mg will act in this direction. If I take the component of T2, then this angle is 53 degree. So this component will be T2 cos 53 degree, and this component will be T2 sin 53 degree. Similarly, if I take the component of T1, then this angle is 37 degree. So this angle is also 37 degree. So the component of T1 in this direction is T1 cos 37 degree, and in vertical upward direction is T1 sin 37 degree. So if I balance the force of x direction or horizontal direction, then I can say that T1 cos 37 degree, that is 4 by 5, is equal to T2 cos 53 degree, that is 3 by 5. So on solving, the value of T1 by T2 comes out to be 3 by 4. So option 1 is the correct answer. Let's move to question number 8. In question number 8, a person stands on a platform and pulley system as shown. The mass of the platform and person are 50 kg and 50 kg respectively. The rope and pulleys are ideal and massless. If the person accelerates upward with an acceleration of 2 meter per second square, then tension T in the rope is, and it is given the question the value of G is 10 meter per second square. So if I draw the free body diagram, then mg will act in this direction, 50 into G, that is 500. Normal will act upward, and tension T will act upward. Since the man is moving upward with an acceleration of 2 meter per second square, so I can write the equation as T plus n minus 500 is equal to mass into acceleration, that is 100. So from here we will get the value of T plus n, that is 600. This is my equation 1. If I draw the free body diagram on the platform, then normal reaction will act in this direction, mg will act in this direction, and 2t will act in this direction. Since the man and platform are in contact, so I can say that the platform is also moving upward with an acceleration of 2 meter per second square. So writing the equation for the platform, 2t minus n minus 500 is equal to mass into acceleration, that is 100. So from here we will get 2t minus n is equal to 600. On solving equation 1 and 2, we will get the value of T, that comes out to be 400 Newton. So option 1 is the correct answer. Let's move to question number 9. In question number 9, a satellite is moving with a constant speed v in a circular orbit around the Earth. An object of mass m is ejected from the satellite. such that it just escapes from the gravitational pull of Earth. At the time of its ejection, the minimum total energy of the object is. So we know that total energy is equal to kinetic energy plus potential energy. And for bound system we know that potential energy is equal to minus 2 times kinetic energy. So when satellite is moving in a circular orbit with a constant speed v, at that instant, so potential energy can be written as minus 2 into half mv square. So it is equal to minus mv square. So at the time of ejection, when the mass m is escaped from the gravitational pull of the Earth, at that moment the kinetic energy of the ejected mass can be written as half into m into escape velocity, that is root 2 times orbital velocity whole square. So it is equal to half mv square. So at that moment the total minimum energy can be written as potential energy, that is minus mv square plus kinetic energy mv square. So it is equal to 0. So option 4 is the correct answer. Let's move to question number 10. In question number 10, a spherically symmetric gravitational system of particles with volume mass density rho varying as rho equal to rho naught r for r is less than equal to capital R and equal to 0 when small r is greater than capital R, where rho naught is a constant. It is given in the question, system of particles are not a rigid body so that some extrinsic mass can move inside the geometrical confinement. Now, a test mass m undergoes a circular motion under the influence of gravitational field generated by the system of particles if KER is the kinetic energy of a test mass at a distance small r, where small r lies between 0 to capital R. From the center of the system of particles, then we have to calculate the kinetic energy at a distance r. So, since the given mass distribution is spherically symmetric, so calculating the mass enclosed in a sphere of radius r, so mass enclosed in a sphere of radius r is equal to rho r, that is rho naught into r, into, if I consider a spherical shell at a distance r, so the volume will be 4 pi r square and dr is the thickness. So if I integrate from small r is equal to 0 to capital R, and on solving this it comes out to be pi into rho naught into r raised to the power 4. So if a mass m is circulating at a distance r, then the required centripetal force must be provided by the gravitational force. So I can write g into mass enclosed, that is pi rho naught into r raised to the power 4 into small m divided by r square, that is the gravitational force, that is equal to the required centripetal force m into v square by r. So from here the value of mv square comes out to be g pi rho naught m into r cube, and the kinetic energy at a distance r can be written as mv square by 2. So it is equal to g pi rho naught m r cube divided by 2. So option 2 is the correct answer. Let's move to question number 11.